Hello, this is Richard Collins. I'm writing a response to your message. Pardon my throat, I'm a little tired. The Horizons web interface is one way to go at this. They have, for many things, you can do some rough calculations here. Like for instance here I'm generating an observer table from the sun to a particular location. The one I have is the superconducting gravimeter location, and I can change that here to be the one that you gave me, which was 114.4077, and 30.5228, and I think we're both at 80 meters. Let's see, you didn't give me a height, so I'll just use 80 meters. We can change it anyway. So now this is going to be the only quantity I'm getting in this particular calculation is the one-way range, and the units which I set down here are in kilometers per second, the range units in kilometers. Yeah, I don't want astronomical units. I'm going to put it into a comma-separated value file, and I'm including the data on the object in this, which in this case is the sun. Okay, so this is going to be the distance. It's just going to give us a table of the distance from the sun to the station for this time period. Now you can change this. I'll show you. I did these for 1 minute steps. I presume you can do a calculation in 1 minute. If you come to your best estimate for that, then you can compare it to this. You can also do it in equal intervals and do it by seconds. If you go to do second data or sub-second data, like for instance, 60 hertz sampling on seismometers, or I'm trying to remember all the different sampling rates that I found in the different seismometers. I think they go to 100 samples per second, 10 is common, that sort of thing. If you do that, then you have to use the Horizon JPL software and data tables, the Chebyshev polynomials themselves, let me just run through this just to show you. So this is from the observer at this location to this from the sun, the distance for a particular period of time, just doing range in kilometers and all. You generate the ephemeris, and I'm just going to do this. Let's see, this was the distance from the sun to the earth. This was the nano G experiment, and this is a comma separated value file. So that's the distance from the sun to the station. I call that X is the station for the nano G experiment. I'm going to save that here for a minute. Save that. Okay, so now that was the one I got there. We can change the location to the moon. Just say moon and search, and select Luna. Okay, and then generate that one, and then put this in. This is the R from the moon to the location. All right. Now we need to do this to the center of the Earth in each case. We're at the moon now, so let's just change this to the location Earth. Okay. Search for that. Okay. Oops. I had trouble with this. Oh, cancel that. Sorry. All right. So I'm going to change the target. Oh, I see. It changed my look. I want this to be the center there. There's a trick in here. Let's see. $3.99. Let's see. No. All right, one more time. Oh, at $3.99. Do you know it took me months to learn this thing? So you're getting a boost here. Okay, so 500. Oh, okay. Geocentric 500. I think that's what it was. So I should have read the things again. So here now we're going to go from the moon to the center of the Earth. All the same things. So let's generate that one and do this. Now it's from the moon to the Earth. I name these things really consistently. Okay. Normally I use a program to do this, but I wanted to show you where you can get this data right now without me having to rewrite my program for whatever language, computer language you might be using. And finally, let's change this to the sun, to the center of the Earth. Generate that one. And put this in sun to the Earth. So now I did a calculation for you earlier based on just for the magnitude. I just wanted to see what the signal looked like there. So here, this is what it looks like at that other station, and it's based off of those four distances here, from the sun to the center of the Earth, the moon to the center of the Earth, from the sun to the station, from the moon to the station. Those are the distances you need for the magnitude. If you're doing a full vector thing, then you would do the three components of the vector from the sun to the Earth, the 3 from the moon to the Earth, the 3 from the sun to the station, the 3 from the sun to from the moon to the station, and then you go through the usual issues. I just wanted to show you the apparent magnitude of this, which is going to be spread in different directions. So you'll be like here, it'll probably not be much. These are in meters per second squared. So this is 10 to the minus meters per second squared. Sorry. So these are this is 1,000 nanometers roughly, peak to peak, or 2,000 nanometers per second squared, peak to peak. So that's the thing. Now the thing is if it's all vertical, you'll have it'll affect your vertical signal. If it's all horizontal, it depends on the direction that it's pointing, whether it's north or east or whatever. In general, you have north, east, and vertical components of the thing. And so, and they can point up and down, east and west, north and south. But generally, it's imagine that there's this, this signal there, and it's pointing in whatever direction. So to get, I'm using up 10 minutes here. I don't want to make this too long. Okay, so let me complete let's do this. Here's the nano-G experiment, the sun to the station, and oops, here. Okay, this is what the raw data looks like, and all I'm going to do is pull this column out. I'm just copying this. This is the sun to the station. So I go to here, sun to the station. That's this one, and I'm just going to write over that number. Let me change the format on it here so you can see that's realistic. I don't quite have the number. Okay, that was the sun. We need the moon at the station. So let me go back here. Moon at the station. Let's grab this one. These are and back to here. Moon at the station. And again, I want to put out the decimals till that's roughly the precision that they maintain. So they use 16 bits, or 16 digits, 16 digits when they're doing these calculations. I started way back when, in the 1970s is when I started doing orbital calculations. I worked for NASA a little bit on their gravity models and also satellite tracking. So that's where I learned some of this stuff. Let me go here. I'm sorry, I need to finish real quick. So here's the moon at the Earth. And the sun at the Earth. Okay, now I already had these in here, and what this is, okay, to calculate this signal, it took me the better part of 2 years to convince myself that this was actually the way gravity worked. You know, the GMM over R squared. So this term here is the differential gravity signal of the sun at the station minus the sun at the center of the Earth. And if you can read this, it's the 1 over R squared for the sun to the station, and then 1 over R minus 1 over R squared from the sun to the center of the Earth. And for units purposes, these are in kilometers. Then I have kilometers squared in here. I divide by 1,000, so all my units end up in meters. Okay, so that piece is 10 to the minus 7th meters per second squared. So multiply by 10 to the 9th. So this is 182 nanometers per second squared. Did I get that right? Yeah. Okay. Down, and it's down here, or piecewise. Okay, the moon portion is exactly the same thing. It's the moon at the station, so GMM over R squared, simple Newtonian gravity, that at the station minus the moon at the center of the Earth. So what you're doing is simply subtracting off the gravity at the you're looking at the acceleration at the station and then you're subtracting off the acceleration of the same body for the Earth. So that differential acceleration is just these terms here. So g and then you simply add them together. So this one is now corrected. I just basically went through and updated an estimate of the magnitude of the signal at the station. So now the trick of it is I need to do the full vector calculation to go in and show you what the north, east, and vertical components are for each of those. And this will give you an idea what I had to go through. At the time I did this, the only language I could use that would work well enough was Pascal. And so these old programs in Pascal show you what's involved in doing this. So for instance, let me see if I can get you a few of these things. A lot of this is just, setting. I need unit vectors, x, y, and z unit vectors at the station. So I needed some basic vector calculations. I need the ability to multiply vectors and rotate them. Very simple stuff. Tedious. Takes a while. When you're calculating these gravities, they're just, they're very simple. It's gm over r squared, and it that's all that it takes. And then the trick of it is to get them into unit vector form. So you take those and put them in the you take, basically that's the you see this magnitude over here will get multiplied by a unit vector that tells which way this thing is going. So all of these this basically, we just need to project these magnitudes into this direction. Now a lot of mechanics just reading different files, and let's see. Oh, I did this so you can calculate from that ephemeris or directly from there. The station location was tedious and difficult also. Basically, I rotated the Earth. It comes down to fairly simple things. You can recognize some simple 3D rotations in here. I used a standard Earth here with a flattening. This is a standard Earth ellipsoid, standard Earth coordinates there. These are then geodetic latitude and longitude corrections, and then basically I find out how to rotate the resulting vector, to get it to the correct location. Like I say, it's tedious to get these things right. Okay. Oh, this is northeast and vertical calculation. So again, you use the standard things, standard approaches, and then you can just, vector calculation of the north, east, and vertical component. Okay. This is the standard method for the estimating long-term changes in the Earth rotation angle. If you get serious about this, you go to the Earth rotation service and you get the daily or momentary estimates of the Earth's rotation rate, which might change even during your session if you have a long period. This is the actual gravity calculation. So you see these here. The the distance from the Earth to the Sun, the distance from the Earth to the Moon, the distance from the station to the Sun, the distance from the station to the Moon, the gravity from, let's see, I'll have to go back and look. Oh, this is the gravity from the Earth, on the Earth from the Sun, gravity on the center of the Earth from the Moon, gravity from the station, at the station from the Sun, the gravity at the station from the Moon, and then the differences, and then simply you add them back together again. So this all, basically, I did this calculation here in vector form. So it's again tedious, but not horrible. The regression, as in the spreadsheet that I sent you, was, let's see, oops, wrong one. Okay, in this calculation here, this is what I sent you before. This is actually the Wuhan data. This here, this column. This is the Julian date for it. So these are the actual nanometers per second squared at their vertical, and this is the calculated value, and this is the this here is the gravity, the vertical gravity signal calculated, and this is what it's if you see, it's a linear regression between this station data and the gravity calculation. So when I do those vector calculations, they end up being this column here. All you see is the number, but that's what all that program was doing, is calculating this gravity. And then I simply regress those two to find a intercept that is an offset and a multiplier. So I multiplied this number here by 1.17, this factor, and then add, or in this case, add a minus 467, so on, to get the calculated value. Then I plot these two together, the actual against this regressed or corrected one. This is what I call a calibrated number, and then it shows me, basically, I can take the gravity and generate what signal you're probably going to get. Likewise, I can correct this, which is a nominal value at the station, and convert it into an estimate of the actual gravity, put it into absolute units. I think that's the important thing here, is that you want to have this in absolute units. So this, I had to blow this up, and even here it's hard to see. This is about 20 days, I guess, of this signal. So it gets this complex, the vertical signal, because the sun and the moon are moving and the earth's rotating. It's a mess. This is just this first part here. Says I just blew this up, and if you just look real close, you can see a little tiny bit of the blue showing, and that's because I made a mistake in, I think I need to add in the centrifugal force of the station around the Earth-Moon barycenter. I didn't do that. It only occurred to me later, and so I need to correct that, but I should be able to take out that small little bit of blue in there. And you see the regression coefficients, the R squared here, 0.9998. Now, in my I'm a senior mathematical statistician. In my statistical life, that is rare that you get such a good match on something. And so these quiet time signals give you a very solid way to connect the Newtonian gravity at the station with the signal from something like a superconducting gravimeter. I don't have time here. I can make you another video if you want to know about what I ran into with the seismometers. But those signals are noisy, and yet I was able to essentially do the same thing. Their horizontal signals were even noisier because they had relatively small test masses and all. If you guys do a large flat plate experiment and track it closely, the second derivative of the plate position, the plate position of the center of mass of the plate should follow, if it's like oriented north and east, north and south. So if you have a plate, along the north-south axis, then it will pick up the gravity signal for the horizontal east and west signal. So, and if you have a plate that runs east and west, it will pick up the north-south gravity signal, and those should be pretty stable. The larger your mass, I think, the larger your mass, if there's some trade-offs in there, but you should be able to get some good a good horizontal thing. Now, if you're doing it with MEMS, I'd really love to see some of the data that you get. If you can push your MEMS gravimeters to get into this ballpark, this is plus or minus 1,000 nanometers per second squared. If you can get into that range where you can see a signal at any precision, so amplify your signal in here, break it into as many pieces as you can, and then look at it. If it goes outside this range, if there's earthquakes and other things, you can. I found ways to remove that for the most part. Anyway, the thing is you can calibrate any gravimeter absolutely this way. So whether it's vertical, horizontal, even some odd geometry I hadn't seen yet, you can probably figure out what the impact is. It's very simple physics, very difficult, tedious programming and number crunching and figuring out all of the special codes that you need to know along the way. But I think it's worthwhile. Anyway, I'll help you as much as possible if you would like. Thank you.